Hello everyone, thanks to everyone for watching this video. My name is Qidang. I am an architect and engineer. Today's video is titled Unreinforced Arches, and it is going to introduce the Hooke's curve and the Inglis curve. I am going to give you an overview of what I am covering today's video. First at all, it is a bit of background to the topic, and then focus on the arch only and the backfilled arches. A masonry arch is a curved structural element that spans an opening. It is able to sustain loads solely by compressions. It is a structure whose geometry, perhaps better than any other, epitomizes the ingenuity of masonry constructions. In order to erect an arch with bricks or stone voussoirs, the individual masonry elements must be placed with radial joints to prevent shear slippage. The research conducted by Robert Hooke at Cambridge led to formulation of the resistant model of the arch, using the funicular curve of the loads. The arch, whose axis is upside down with respect to hanging chain, catenary, can sustain the same loads, determining the equilibrium curve of the chain. In 1675, Hooke realized the importance of studying upside down or inverted systems to analyze the equilibrium of masonry arches. It is worthwhile deriving the equation of the catenary. This figure shows an element, the S of the chain, in equilibrium under its own weight and axial tensile forces acting along the tangents to the end sections of the element. The problem is to determine the equilibrium curve Z equal to Zx of the chain, where x indicates the horizontal abscissa. The function z equal to zx, which is defining the horizontal projections of the ends of the chain, varies between the values of 0 and L. Moreover, we assume that z equal to 0 and x equal to 0. Let g be the weight per unit length of the chain with constant cross-section. Each segment ds weighs g times ds. The horizontal component of the tensile force N in the chain is constant, while the variation along x of its vertical component equals the weight of the element ds of the chain. Thus, we have the two equations, where theta indicates the angle between the tangent to the catenary and the horizontal axis x. The horizontal component of the pull N in the chain is denoted by h and is given by h equal to n times cosine theta. Therefore, combining these equations, we can obtain this expression. Because ds times cosine theta equal to dx, we can obtain h over cosine theta times d theta over ds equal to g. Splitting the variables and integrating gives this expression. Under the assumption that, by symmetry, the origin x equal to 0 is found at the middle of the chain, so that for x equal to 0, we have theta equal to 0. Integration of the left-hand side can be obtained as this mathematical derivation. The integration is expressed here. Then we can create an equation to find a relationship between tangent theta and x. Because tangent theta is equal to dz over dx, we get this equation. Using the hyperbolic function cos x and taking into account that z equal to 0 and x equal to 0, we finally obtain here. This equation defines the segment AHC of the chain drawn in the Hooke's curve. Once function z equal to zx has been determined, the pull h can be evaluated. In addition to the weight of the arch, there are also the weights of the filling material, the spandrels, the road bed, and any ballast, which as dead loads should be taken into account in the arch design. This problem was studied by Inglis in 1863. This figure shows a voussoir arch supporting a level roadway. The field is supposed to be of uniform density and to impose a purely vertical load on the arch ring. If the origin of coordinates is taken in the road surface on the center line of the arch, and the equation of the arch center line is zx, then the intensity of vertical load per unit horizontal length is gamma times zx, where gamma is the unit weight of the arch and fill materials. The problem posed by Inglis is the determination of the arch center line, so that it coincides with the thrust line resulting from this dead loading. That is, each element of the arch ring will be subject to the forces. From this figure, we can write the differential equations of equilibrium. The horizontal component of the abutment thrust N is constant. Then we obtain this equation. Because tangent theta equal to dz over dx, we can obtain the second-order ordinary differential equation, where alpha equal to gamma over h. After the mathematical derivation, and consider the depth of the fill at the crown is c, so that we obtain this equation. If the rise of the arch is f, then we obtain the expression of alpha. Substitute the expression of alpha into the previous equation of zx. Finally, the required equation of the arch center line becomes this expression. This equation represents a family of curves with parameter f, and corresponds to the infinite number of possible positions for the thrust line. A practical design could specify the span L and a total height c plus f, but the value of f itself could be chosen by the designer. From conclusions, what we learned: the arch ring is a curved course of masonry, which supports loads principally in compression. The line of thrust is a theoretical line that through the structure represents the path of the resultants of the compressive forces. For a structure to be stable, the line of thrust must lie entirely inside the structure. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching,